say something then. Okay. All right. Before we get started today, there's two, and I know you've heard these, but I want to make sure everybody has an opportunity to hear them. Two pretty major announcements that I wanted to put on Screencast-O-Matic. The first of these is almost too late to do anything about it by the time this loads and you get to hear it. But today, Wednesday, the 30th of November, 2016, is the last day that you can withdraw from a class. And, you know, if you feel like you're hopelessly behind, there's no way you can complete a course. And this isn't just you. If you know of friends, classmates, other people that may be in this boat, please help them out. If you are hopelessly, or they are hopelessly behind in a course, no way you don't think you can pull anything above a D out of the course, then I see no disadvantage at all in withdrawing. The only things they talk about disadvantages of withdrawing are financial aid. But look, if you're going to make a D or an F in a course, you're going to have to take it again anyway, and it lowers your grade point average. You might say, well, it slows down my graduation. If you make a D or an F, you're going to have to take it again. It'll slow down your graduation, and it'll lower your GPA. So there is no, that I can see, negative side to withdrawing. I mean, it doesn't hurt you academically at all, and any of the negative impacts it has on completions and financial aid and stuff, you're going to have those same problems if you make a D or an F. So why mess up your grade point when you don't have to? So please consider that. Okay, again, it's not necessarily for y'all. Y'all are pretty far along. But the other folks, okay, that you might be in contact with, please let them know. Encourage them. Better than making a bad grade. Because fixing that on your raising your GPA sometimes is a hard thing to do. All right, the other thing is they have now opened the student course evaluations. Hopefully you've read your emails and seen this. Maybe have already done it, but even if you haven't already done it, please do so. Now, you have till the end of the term, so there's no urgency on this one, but please don't wait till the end of the term and then forget it. Please do the student course evaluations, because in addition to this course or other courses you're in, you're also asked to do a few other surveys, and sometimes those are the only inputs of feedback that those folks get. So please do your student course evaluations. You heard that, right? All right, good deal. All right, any questions? Did you have one?
I was trying to find something similar to number 7 on the test, but I'm kind of struggling.
Okay, let me see if I can find number 7 on the test.
I can show you mine.
Well, just so I have something to look at here.
I think
This-
I kind of got the steps.
Is this test 2?
Yeah.
Okay, test 7, find the unit normal vector, unit vector in,
Then the curvature K.
the curvature K, kappa.
Center of the oscillating circle at R0 for the curve RT, blah, blah, blah.
Right, okay. Now,
Find something similar to what we work out.
all right, let me,
That's the last one I have to do.
all right, this is in chapter 13.
Yeah, I have it marked in section 13.4.
Yeah, that's where I am. And, okay, Matt's here. All right, the finding the unit normal vector, that's example 5 on page 715. That was 2-dimensional rather than 3, but no, it's 3-dimensional. Find the unit normal vector.
I almost feel like example 7. You see that one yet?
Okay, yeah, I was going there. I was going to say that next. That would be
Just
parameterizing the osculating circle.
But if we went up to step 3 and
Yeah, find the center Q. That's it exactly. Now that's a two-dimensional. This is three-dimensional.
but of course they have something different is given, and it has 2-dimensional, right?
Right. And the kappa is I know we've done that.
Yeah, it's
The curvature back, that is
f double prime over 1 plus f
right.
prime squared to 3 halves.
Yeah.
I think I actually did.
And example 3, well, let's see. Yeah, example 3 gives you shows how to get kappa. And example 4 shows you how to get kappa at different points. So there's not one example that shows all three, but well, in reality, that example 7 does show it's just a two-dimensional though.
This step from going from K to N is a little bit simpler in the plane versus in 360.
Yeah, definitely.
I think that's the part where I was kind of struggling, going from T
Okay.
prime, I guess.
Yeah.
To,
Okay.
that's kind of what I was trying to
I think the thing that might help you out a little bit is I hesitate to say this, but I think I'm correct on it, is if you notice that when t is equal to 0, your curve r of t is e to the t 0 t squared plus 1. Well, I've plugged in the 0 for the middle. So basically, it does turn out being a plane curve there. I think that would help. It's the xz plane, not the xy plane. And example 8 also, it's talking about the osculating plane. I was going to say that, but that's, that one is there. It's just a little messier, but in this case, you're actually in a plane because at when t is equal to 0, the y value is 0, so meaning that you're in the xz plane. So I think you can do it there. Things will be in terms of x and z. Is that enough, or?
I think that should help.
Okay. Any other questions? All right. Okay. Let's hope you're getting everything lost in that and not being able to find it again. Okay, I think I marked all three of you here. So, if there are no other questions, where we left off last time was on page 760 in the new edition, very bottom of that page, higher partial derivatives. Now, we did this figure 4, but I wanted to do a little bit of stuff before we got to theorem 1 because that's the next thing on the slide set. There's several things in between here, and I actually will have more room writing here, so I think I'll do this. The higher order partial derivatives are derivatives of derivatives, just like they were in 2-space, okay? They are here as well. Well, when I say 2-space, strictly 2-space. One, single variable calculus, single independent variable. When you have more than one, you just take, just like before, derivatives of derivatives, but now you can take, okay, the second order partial derivatives of f are the partial derivatives. Say you have f, whoops, let me get my pen. Okay, let's say we have some function f is a function of x and y as independent variables. Okay, if that's the case, you can take the partial of f with respect to x and the partial of f with respect to y. Those are your first order partial derivatives. Now what you can do, you can take the partial of f with respect to x again, or you could take the partial of f with respect to x and take it with respect to y. You could take the partial with respect to y and take its partial with respect to x, or x partial with respect to y. I'm sorry. I get to talking and the writing goes awry. Okay. Partial y with respect to y. So whereas if it's a two variable situation, two independent variables, you can take two first order partials, but then four second order partials, okay? Because you can take the partial of the first with respect to either one of the two variables and the partial of the second with respect to either one of the two variables. And certainly if that was a three variable case, then you have three first order partials and then 3, 6, 9 second order partials. So they just keep getting bigger. And then you go to the third order, fourth order, and they just keep multiplying like rabbits. Okay. Now, one thing I wanted to mention here is this, the notation. To me, this is a simple way to express partial derivatives. Put the subscript of the variable you're taking the partial with respect to. Okay? Easiest to write. But in the sort of like Leibniz notation, what this one would have been was partial of f with respect to x. And this one would have been partial of f with respect to y. Now up here, in this notation, the easy notation, you're taking the partial of this thing with respect to x, of that thing with respect to y, of this thing with respect to... But if you're doing it down here, remember you go from the left, not to the right. Okay? So this would be if you're taking the partial of this, partial of f with respect to x, with respect to x. Now, it's hard to tell with the x's because they're both x's. That would be this one, of course. But if you did it the other way, the partial with respect to y of the partial of f with respect to x, that's this one. Okay? Now notice up here, it's xy. Down here in the order, you see yx. Because you're taking the partial of this thing with respect to y. That's what this is saying. You're taking the partial of this thing with respect to y. This one, the y follows, this the y precedes. Okay? So don't let that cross you up. Okay? And neither let me confuse you with it. Okay? So this one then, tell me what that one would look like. Partial with respect to x of the partial of f with respect to y. And by the way, that's why I'll come back to that in a second. Okay? And then the last one would be okay, got it. Now, what's that? Yeah, you just have to call it partial. The sort of shorthand notation for this, not as short as that is, that's d2f dx squared. It's not dx squared, but dx, or it's not really a d, partial x. And then this one would be partial 2f over partial y partial x, okay, and so on. So there is another shorthand that you don't have to quite write quite as much as this, but it's still, the order matters. This order and this order are the same. You can just simplify ever so slightly, mostly removing parentheses and putting a square there. But that is a far easier notation in my mind. So, and they're both clear as long as you realize you have to look at them differently. Okay. And since they wrote them all in, I guess I should too. This one would be d2f partial y partial f partial x. This is partial 2f partial x partial y. And this is partial 2f partial y partial y. Oh, well, that one you can just write y squared. Now, but we say y squared, but it's not y squared. It's partial y squared. Okay? It looks like it's partial y squared. It's not the partial of y squared. It's partial y squared. Because that is its own entity here. That's the thing. Because you never see that bottom one that doesn't have the symbol with it. The top one you see the symbol operating on something else. Okay. That done. Any questions on that? It's just not notation is all that is. So let's do example 7. Calculate the second partials of I say second partials of and then I write second partial. Okay, but let's not do that. Oh, that's easier. Okay. The second partials of f of xy, two variable independent variables, equal x cubed plus y squared e to the x. What you got to do first? Yeah, you got to do the first partials first. Okay, so let's do those. What would that be? Partial of f with respect to what you want to do first. X with respect to x would then be 3x squared plus y squared e to the x. Perfect. How about the other one? Partial of f with respect to y would be, the first one would be 0. 2y e to the x. Got it. Okay? Yeah, I would do it that way, but I was doing it however you said it. I'll do it. Doesn't matter. It doesn't matter because they put the y's first on the first one. It doesn't really matter. Okay. Now it asks, though, for the second partials. So which second partial are you going to do first? Okay, second partial of f with respect to x twice. Very good. What partial you want to do next? Both. Okay, this one over here. Second partial of f with respect to y twice. Okay, and that would be done. Those are the only two second partials? Second order partials? Yeah, and we better. So let's mix them up. Which one you want to do next? Okay. I've been writing them like this because they had written them above like this, but then they turn around and do the second partials with the simpler note. Well, they do them both ways. It doesn't matter. Which way you want to do it? Okay. So f, x, y. Okay. Now, by the way, just for the book's doing this too, this is the second partial. This is partial with respect to y of the partial of f with respect to x. So that helps you see it maybe a little bit better, but the other one sure is a lot easier to write. Okay. What would that be? Yeah, 2y e to the x. Very good. Okay, f sub y sub x, which is the partial with respect to x of the partial of f with respect to y, which would be, okay, no, the partial of this thing with respect to x. Yeah. To y e to the x. Okay, nothing too much changed there, did it? But the thing to note is that these two are exactly the same. Now, it just happens to be these two are the same too, but that's just because you had e to the x in there, and that's just what happens with e to the x. But down here, going two different ways, you got your cross partials, is what I'm going to call them now, to be exactly the same. Okay? Uh-huh.
We were going and taking the partial derivative with respect to y of the very first partial.
Yeah.
Yeah. See, I was
This one,
mesmerized.
yeah, you're doing partial with respect to y of f sub x. This is f sub x. Taking that with respect to y would be no y's there, so that's a 0. So you just like that and got that one, huh?
Yeah.
Yeah. Okay.
I was looking at the wrong one.
Okay.
But yeah, it's supposed to go all the way up to the
Yeah,
top.
you were looking at that one, and it came out the same thing.
Yeah.
Okay. Boy,
Boy.
count your blessings. Okay.
I could have just said that.
All right. But let's do example 8, and then we'll come back and do maybe a little bit of generalization here. Can I take this off? Okay. Example 8. Calculate f sub x, y, y for f of x, y equal to, well, that looks familiar, doesn't it? X cubed, why did I erase what I had, plus y squared e to the x. I will fake it then. I'm going to write down what we had so far. We had f sub xy for that same function. We had to be 2y e to the x, wasn't it? Okay? Now we take that with respect to y again, so f sub x y is equal to 2e to the x. Got it. Good deal. Now, that was pretty easy. Okay. And by the way, partial derivatives are pretty easy. I mean, if you think it's just been happenstance, no, they are pretty easy. All right. So here's Clairaut's theorem. Okay. And by the way, for those who haven't done a paper yet, or haven't even selected a topic for a paper yet, here's another one, or two, or three. Who in the world was Clairaut? That could be a paper topic, maybe not quite in those terms. Okay? How did he come about developing this theorem? That could be a paper topic. Or what are some practical applications or uses of this theorem, if you can find some of those to do. We'll see. But here's what it is, the equality of mixed partials. Now, if f sub xy and f sub yx are both continuous functions on that disk D. Remember, the disk D defines the domain of both x and y at the same time, okay, because those are independent variables. So now, rather than having an interval on the line, you have a circle, a disk, around some point, okay? So if these are both continuous functions, both the second partials, both ways are continuous functions on the same disk, D, then f of sub xy evaluated at AB that is somewhere on that disk is always equal to f sub yx at that same AB, as long as AB is in that disk. Okay? In other words, your second partial of f with respect to y then with respect to x is equal to the second partial of f with respect to x then with respect to y, as long as both of those partials are continuous on the disk that contains the point AB, where you're trying to evaluate. So you might have a partial that blows up at 0, but as long as you're looking at it out here at 7,3, you know, somewhere not that far from 0, but not 0, they're continuous. Both of them are continuous there. No sweat, they will be equal, whichever order you do the mixed partial. Which is a very nice thing if one of them's really nasty, and doing it the other way, you can avoid some nastiness. Avoid the nastiness, okay? Because as long as they're continuous in both directions.
Or if you absent mindedly accidentally do them backwards.
What's that? Yeah, exactly. That might help too. So,
Oh, hey, there's more about it.
let's do example 9. Now this is actually an equation you do run into in physics. They're asking you if what the second partial of W with respect to T first and then with respect to U is equal to the second partial of W with respect to U first and then with respect to T. Okay? Now this is and this is for this function. W is equal to e to the U over T. Now, I was going to say that this is something that you run into in physics, but usually in physics that capital W is work, and U is usually potential energy, and T is usually temperature. And frankly, I don't see there's any way in the world that could make any sense. Okay, so maybe you don't run into this in reality. I think with a constant out in front, that could be the case if the constant absorbs the units. But then even the U and the T, they'd have to have the same units. One may be potential energy and one may be kinetic energy. But I don't recognize that as a formula anywhere. So at first I thought it was, but it may or may not be. I don't know if it is. Jonathan's here. See in this bright light. Okay, we're at the top of page 762. This is in the new text. Yeah. Are you in the new or old? Huh? Okay, yeah, it's in section 14.3, partial derivatives, example 9. Okay? All right. And by the way, I should have flipped over one page. Here is a picture, a painting, I don't know what it is, lithograph or something, of Clairaut. Alexis Clairaut lived a pretty short 52 years, somewhat sad. Brilliant French mathematician, presented his first paper to the Paris Academy of Sciences, and this was probably one of the premier scientific organizations on the planet at the time, at the age of 13. Okay, I would say he was a pretty brilliant kid. Okay, in 52 he won a prize for an essay on lunar motion. And by the way, 52 he was still 39 years old, right? Yeah. That Euler praised, and it says surely an exaggeration, as the most important and profound discovery that has ever been made in mathematics. Probably rubbing it in a little bit too much, but still, he must have been pretty highly impressed. Okay. Yeah, I heard that too. Okay. And by the way, Euler is another potential paper topic if you hadn't noticed that before. Or you could even, if you can find his essay on lunar motion, find out what was so special about it, or, yeah, whatever. Okay. But let's go back. Okay. So So what we're asked to do is show that those partials are indeed equal. Clairaut's theorem says they should be. Let's see if they are. What do we have to do first? Partial of W with respect to U, if you want to. That's no sweat there. And what would that be? If it would help, I can volunteer to take the partial of E. I'll be glad to. Okay. Part of it is going to be E to the U over T. Oh, that was the hard part. Okay, you're absolutely right. Times the partial of this with respect to U would be 1 over T. So you could write it that either way. Okay. I thought you just needed a little nudge. Now, before I do the next first partial, I'm going to rewrite this as E to the U T to the minus 1. Because to me, that's easier to do. Okay? Now, what do you want to do next? Of W, partial of W with respect to T. And that would be what? E to the U over T. Yeah, you could put minus 1, but I'm going to go back and say it that way. Times. Yeah, the U is like a coefficient because it's held constant. So yeah, I'll put the U here. I'll put U there. Okay. T squared is going to be in the bottom. One more little thing. When you take the derivative of this with respect to T, it's minus 1 U T to the minus 2. The minus 2 is why that one's up at the bottom, but don't forget the minus sign there. Okay? All right. I hope the dentist is through here. Okay. Now, what do you want to do next? Okay. You know, I've written something wrong here, and nobody said a word. Okay. Okay, if you go back to this one here, is that what you mean by the first one? Over here. Okay, so if you're going to do that one first, you go to the second one we did there. Right. And then take the partial of that with respect to U. Because you're taking the partial with respect to U of the partial of W with respect to T, which is what that was. Okay, so you want to do that next. So you want to do the partial of this with respect to U, which is the partial of this, which has to include the minus sign with respect to U. I know it's awfully crowded there. Okay? And if you're doing that with respect to U, I think we're okay. So let's bring this down here. Let's bring it down here and spell it out a little cleaner. The partial with respect to U of the partial W with respect to T is equal to partial with respect to U of minus U over T squared e to the u over t. There, that's a little easier to see. I hope I wrote it right. So let's do that. What is that? Say that again.
Bringing the t and the exponent down below again, right? So
Yeah. Minus u over t cubed e to the u over t. I don't know how you like to do your chain rule. I like to do the big function first and then, wait. We have a product rule here, don't we? Yeah, we have a product rule. So this is part of the product rule. When you take the first times the derivative of the second, that gives you this. Okay, derivative of this with respect to u would be e to the u over t times 1 over t multiplied by this, and that's what you get. That's part of it. What's the other part of your product rule? Okay, minus 1 over t squared u to the u over t. That's the derivative of the first with respect to u times the second. Okay? Now, I'm happy with that form if you are. Okay? Or you could do some simplification by pulling out minus 1 over t squared e to the u over t, and then that would leave you times u plus u over t plus 1. If you want to do that, I don't see that as all that simpler, but you could do that. All right? What else have we got to do? You got the left-hand side up there done. Now let's do the right-hand side. How do we do that? To t, no, with respect to t of that. Okay, yeah. So take the partial of this with respect to t, which is the partial of this with respect to t. Oh, that's ugly. So that would then be partial of t partial of w with respect to u would be, and guess what? Another, well, I'd call it a product rule. Since we're taking with respect to t, let me go up, with your permission, and write this a little differently. Let's write that 1 over t and the u over t, let's write that as t to the minus 1, ut to the minus 1. And it's only the t that's to the minus 1 there. I know that's a little ugly there, so let me see if I can clean this up ever so slightly. Okay, I don't know if that's much better, but a little bit. So let's take that partial, and what do you get? Minus, second. Okay, so I'm going to write that negative 1 over t squared. Is that okay? Okay. Over t. Okay, can I go back and write it like that? Whatever rocks my boat, right? Okay. Next. Okay, I'm going to put a plus there. I'll write it t to the minus 1, okay. Okay. All right, let's either put the t down there or not use negatives, one or the other, but let's not do them twice, okay? So t to the minus 1 times the derivative of this with respect to t. That would be e to the u over t. That's that part. Times derivative of u t to the minus 1 with respect to t would be a minus u t to the minus 2. Okay. Now, I did mix them up some there. But you see, that's where the minus sign comes here. And you have a 1 over t here and a 1 over t squared there. So that gives you a u over t cubed e to the u over t. Okay, I left the first term because we'd already finished with that. And let's see what we've got here. This term here is identical to that term there. Good, good, good. And this term here is identical to that term there. Drum roll, please. Okay. So sure enough, they are equal. Now, if indeed those were, if that was indeed somehow temperature, which the SI unit for temperature is the scale for temperature is the Kelvin scale, absolute zero. By the third law of thermodynamics, you can approach but never reach zero on the absolute scale. So that would be defined everywhere except zero. Everywhere zero and above, and on the absolute scale, your temperature is always above zero. So everywhere those temperatures are allowed, which are greater than zero, that would be fine. And indeed, they are the same. Now, if that T stands for something else, like maybe kinetic energy, I guess that could be zeros. You just have to exclude that from your domain. This would have to be in the disk that does not contain origin, or zero for whatever the T stands for. All right. That one okay? Now, although Clairaut's theorem, and by the way, they do have it in the book too, and they write on all the T's as exponents, with negative exponents. So they start with negative, let's see if I, yeah, that's it. Negative t to the minus 2 e to the u over t, which is the same as our second term there, minus u to the t to the u t to the minus 3 e to the u over t. So yeah, that one works. And then when they did it the other way, they also had minus t to the minus 2 e to the u over t minus u t to the minus 3 e to the u over t. Yeah. So they put the u over t's in the exponent as denominators, and they put them as exponents in the other part. So, okay, whichever way you want to. Now, although Clairaut's theorem is stated for f of xy and f of yx, f sub yx, partials, second partials in reverse orders. I call them the cross partials. I don't know if that's a good name for them or not. It implies more generally that partial differentiation may be carried out in any order, provided that the derivatives in questions are continuous. And they say, see exercise 75. You can see it now or see it later, but you'll see it, okay. For example, we can compute f sub xy by differentiating f twice with respect to x, twice with respect to y, in any order whatsoever. So what that's saying in shorthand is this. F sub xy is the same as f sub xy, which is the same as f sub x YYX, which is the same as f sub YYXX, which is the same as f sub YXXY, which is the same as f sub YXYX. I think I've got every possible combination down there. 1, 2, 3, 4, 5, 6. 1, 2, 3. Yeah. It doesn't matter what order you do. As long as all those derivatives are continuous, okay, on the domain that you're dealing with. So even though Clairaut only expressed it for 2, for partials, second partials, you can have any number of partials, as long as you have the right number of x's and y's, and don't change that in. The order doesn't matter, but you have to do it. So let's move to example 10, which I think I'll clear out that little bit of writing just in case we need it. Calculate the partial derivative. I can't even read that. It looks like g sub zzwx. Okay. Almost sounds like a radio station, doesn't it? Okay. Where g of xy zw okay, is equal to this very familiar function, x cubed, I'm just kidding, w squared, z squared, plus sine of xy over z squared. Okay, you want to find the partial of z with respect to z, partial of g with respect to z, and that partial with respect to z, and that partial with respect to w, and that partial with respect to x. Okay? How would you begin?
Partial with respect to x.
With x? Sure. Okay, you like to work hard. That's good.
No, let's not.
Okay. W. Why?
Because there's no W in the sign.
And that last thing, and when you take it with respect to w, you lose all meaning there. So why start and do the x first and then the w? Start with the w. Keep it as simple as possible, guys. Okay. I can say guys because, okay, say again. So let's first do g sub w. You can tell Matt's lazy. Okay, just plumb lazy. What would that be then, folks?
Would that be 2?
X cubed.
Z squared?
W is z squared. Okay, it doesn't matter. But that's all it is. Okay? You lost the whole last term because there was no W dependence there at all. So you don't have to mess around with quotient rules. You don't have to mess around with sines and cosines, chain rules, nothing. Lazy guy over there. Okay. What you want to do next?
Which ones do we need to do? We need to do z twice. Next one, let's do x now.
X next, okay. So that'll be g sub w sub x, then would be
6x squared w z squared.
right.
And then we gotta do z twice, so let's do the z next.
Okay. Do them one at a time.
So 12 x squared w z, and then the last one g w x z z.
That does sound like a radio station. Okay.
12x squared w.
All right. Let's see what they got. Hey, look at them. They got it too. Now, the one thing they did differently, and I think I would have been tempted to do it differently too, is because, and it really doesn't matter in this case, this is the lower thing, so I think I would have done the z next, and that would have been 4 x cubed wz. And this is going to be hard to do without, and then do a z again, and you lose the z, and then when you do the x last, you don't even have a z in there. But look, those were all simple. Once you got rid of that sign with the denominators and all that stuff, it didn't matter what you did. Okay, good deal. Any questions on that? Now, they have a quick little blurb at the bottom. A partial differential equation, PDEs by the way, is a differential equation involving functions of several variables and their partial derivatives. A solution to a partial differential equation is a function that satisfies the equation. Oh, how clever. The heat equation in the next example is a PDE, partial differential equation, that models temperature as heat spreads through an object. There are infinitely many solutions, but the particular function, that sounds familiar, doesn't it? In the example describes the temperature at time t greater than 0 along a metal rod when the center point is given a burst of heat at t equals 0, and that's in figure 6 is the graph of that. You gave a sudden burst at time t equals 0, and that gives you the plane first. So that center part, let's see if they have a slide of this. Yeah, there it is. Okay, that sudden burst at time t equals 0, this is where you're beginning here in this plane. That's the curve. You give that sudden burst of temperature here, does that. Well, then the average kinetic energy of the molecules, they bounce into each other. A little bit later, it's a broader curve, and then later it's broader still, and after a while, you can hardly tell anything happened. Okay, as t goes on, finally the temperature sort of equilibrates. Notice it does look like it's increasing a little here, and yeah, that is what's happening. The whole sheet is heating up, and soon the whole thing, this one spike here in the middle, has now dissipated, and the whole sheet is about the same temperature. Now, I'm trying to remember, I can't remember if this actually goes back to Newton or not. I probably should have blown that up, shouldn't I? I know that Newton developed Newton's law of cooling, and it would seem to me on first glance and blush that maybe that's very similar to the law of heating as well. But I can't absolutely swear to that. Okay? But this is the diffusion of a burst of heat over time. Okay. That's what I think the next example is going to be dealing with. The heat equation. Show that equation, u of xt is equal to 1 over 2 times the square root of pi t in the denominator times e to the minus x squared over 4t, defined for t greater than 0, so not at 0. So we can't see quite what happens at t equals 0. And here's a reason for that. At t equals 0, all the heat, all that burst of heat is at that one single point, and it's probably going to infinity there. So this is good, t greater than 0. You can't draw infinity on there, but then sometime after that, this is what you have. Okay? I don't know how big an increment later, but some increment later. Okay. Now I have a feeling that this next blurb, no, okay, that's something else. Okay. Show that this function here satisfies the heat equation. Here is the heat equation. Of course, when I go to write, it's going to reduce in size. The heat equation is that the partial of u with respect to time t is equal to the second partial of u with respect to x squared. Okay? And we want to show that this equation here satisfies that partial derivative, partial differential equation there.
Take it once with respect to
Okay.
t and twice with respect to
Okay, so which we want to do first?
I guess we'll do t, get it out of the way.
Partial of u with respect to t. to get it out of the way would be, now I would write this a little differently. I guess you felt that coming, didn't you? Okay, so let me write this a little differently here, especially for our t part. I would write this as, I think I'd leave the 1/2 there. That's not hurting me at all. And then I would do pi t to the minus 1/2. You buy that? E to the minus x squared times 4t to the minus 1. It's a weird way to write it, but I think it'll make your taking derivatives hopefully a little bit simpler. Maybe somewhat, possibly. Okay, so let's take it. No matter what you got a product rule, right? So where would you begin? The e first, so you're going to write the first one down. 1/2 pi, I'm pretty sure that's a t to the minus 1/2, and then the derivative of that part is, with respect to t, okay. I know there's going to be a minus, so I pulled that out there. Okay. I know there's going to be an e to the minus x squared for t to the minus 1. I know that's going to be in there. Okay. Now that minus came from taking the derivative of the upper part, which is a minus 1.
Oh, that's a 4, not a u.
Huh?
I thought that 4t was a ut.
That's a 4. Okay. Okay. Here's where it starts giving me headaches. Okay. Derivative of the upper part. I put the minus sign up there. Now I'm not convinced I need it. In fact, I think I don't need it. Because the derivative of the second part would be e to the minus x squared t. Okay. Then the derivative of this part would be minus 1 times a minus. So that's going to be a plus. X squared just counts as a constant here because you're taking derivative with respect to t. And then you've got a 4t to the minus 2. Then you have a 4. So I'm going to move my plus sign over just a little bit so I can squeeze my 4 in there. Okay, that's what I think that is. That's just the first term of it, though. Remember? Yeah, we still got to do the second term. And we're going to have to come back and clean that up a little bit, too. The second part of your product rule would then be negative 1/4. Okay, you got a pi, so I'm going to make that pi for us. But then you have a pi t to the negative 3 halves, isn't it? Okay, so that's the derivative of the first part times the second part, e to the minus x squared 4t to the minus 1. Now, this is the part that kind of stinks a little bit, is having to clean it up. And unfortunately, there is a little bit of cleaning that has to be done here. Partial of u with respect to t, and this is a time t here. This is heat equation. Okay. Now, notice everything in that first part there is in the denominator, just as it was there. So that is 1 over 2 times the square root of pi t. Okay. And I put a plus in there as if it's adding. It isn't. Okay. That plus meant it was a negative and it became a positive. That's multiplied by a 4x squared. And then we have down here a 16t squared, right? Okay. And then we have an e to the minus x squared over 4t over 4t. Okay. That's the first term of our two-part thing here. And you notice the 2 here wipes out half of the 4, leaving the 2. Oh, except that, forget that. Let's not do that. The 4 wipes out the 16 down here and left with that. So now we have 8 in the denominator. And I think that's all we can do there. Okay. We'll come back and mess with that later. The second part has a minus. Well, this is where it really gets tricky. I'll go on and put them all in, but then show you how they come out. Pi over 4, and that next term is a 1 over. Now, a pi t to the minus 3 halves, or 1 over pi t to the 3 halves, that would be a pi t times a pi t to the 1/2. Now, the only reason I did that is so I could wipe out some pi's there. Okay? And then this is times e to the minus x squared over 4t. Okay. Now, before I forget what I've done here, which is awfully soon, let me clean this up just by erasing. Okay. We've lost that numerator and the what? No, we didn't. I started to and then decided to change my mind. So that's 2 times 4 is 8 down there. Yeah. So let's just leave it like that for now. If we need to come back and change it, we will. Okay. That was a single side. Let's do the double derivative, second derivative. We got to do the first one first. So let's first do partial of u with respect to x. This u, by the way. Now this time, I see no reason to fiddle around with my t's to the 1/2 and stuff like that because you're not going to deal with them. So what do you have here? Yeah, no, it's really not. That first is a coefficient. Because you're taking with respect to, and no, it's not going to 0. It's a coefficient. It's a constant. So you just write it down. 1 over 2 root pi t. Okay? And derivative of this is e to the minus x squared over 4t. Now we do a chain rule. Derivative of that exponent with respect to x. And that would be negative 2x over 4t. Because over 4t is just like a coefficient. Okay? Which, of course, then you'll lose that. Okay? Now let's see if we can clean that up a little bit. It's going to be a minus, because that minus pulls all the way to the front. And I know we're going to have a 1 over 4. So that takes care of that. And we're going to have the square root of pi t times t. So I'm going to put that other t in front. That t here goes in front. I didn't leave room for it, but it's there. That's your coefficient of e to the minus x squared over 4t. Okay. That's your first derivative of u with respect to x. Is that thing right there? I've lost something. There's an x. The x in the numerator. The denominator is the minus is out front, x in the numerator, 4t root pi t in the denominator. And then e to the minus x squared over 4t. All right, now we're going to take the partial of that thing with respect to x again. Now we got a product rule. We got x in the front and x in the back. But all the x's are in the numerator, so we don't have to worry about the other thing. So what would that be? You tell me. Okay, you're going the derivative of the first. So I'm going, I'm going to put the minus 1 over 4t root pi t. Is that what you were doing? Okay. E to the minus x squared over 4t. Okay, we'll call it it will be a plus. Okay. Ultimately, it will be. It's going to be an x over 4t root pi t. Okay. Times e to the minus x squared over 4t times minus 2x over 4t. Okay, so I already took care of the minus sign because I knew the minus there and that minus were going to wipe out, so I shouldn't have. No. The that okay. Oh, okay. Okay. Tell me your question again.
We're going to multiply that into the x over 4t squared pi t, right?
Right. We're going to multiply numerators. So before we do that, let's take out a 2 here. All right. So your first term's all right. The second term is a plus, and there's an x squared there over 8. Looks like a t squared, a root pi t, e to the minus x squared over 4t. Okay, let's see if these two expressions are the same. All right, this one down here looks more like that one up there, doesn't it? You got an x squared in the numerator. You have a, I know we had it, here we have an 8. 2 times 4 is 8.
8t squared. Yeah.
8. And you have a square root of pi t. And you have an e to, t squared. Yeah, there's a t squared. Right. Yeah, 8t squared, square root of pi t, e to the minus x squared over 4t. Yes, the first term works. The second term would be this one. It's a minus 1 over 4 t root pi t. That's the square root of pi t. Yeah, that's the same. E to the minus x squared over 4t. Yes. Both of them are identical. Maybe not quite in form, but in substance. Does that make sense? So sure enough, this equation satisfies that heat equation. I mean, this function satisfies that heat equation. Okay? Now, it says there's infinitely many answers. That one does. Okay. Aren't you glad to know that? You can run home and sleep better tonight. Okay? Won't you? Okay. Next little thing here is another blurb. Oh, didn't know this one was here. I would have written on this page. No, I wouldn't. I still wouldn't have. Okay, that's the heat equation. Okay, the partial of u with respect to t is the second partial of u with respect to x squared. And in this case, u, I think, is heat. Okay, t is time and x is displacement. Okay, and this is good for positive t's. Doesn't work for negative t's. Doesn't even work for t is equal to 0. Just for that. Okay, but x's go infinitely in both directions, minus infinity to plus infinity. Okay, and that was it. Now, in my book, there's a little blurb called a historical perspective. Do you have this in the old book? Huh? It's historical perspective. It has Joseph Fourier and Adolf Fick. Okay, they didn't show it on the slide. It's a nice little blurb. Remembering this blurb cannot be a source for your paper, but it's a source for an idea for the paper. You could write, and who in the world was Joseph Fourier? A pretty interesting character, by the way. Adolf Fick, I don't know him as well. Fick was born the year before Fourier died, so they never had any really good interaction at all. 1-year-olds don't usually mess around with senior scientists, okay? And this general heat equation was first introduced by the French mathematician Jean-Baptiste Joseph Fourier. Okay, he was debating whether to enter the priesthood or pursue mathematics. I know that's been a struggle for all of you too, right? One or the other. Which way are we going to go here? Okay, yesterday was my he wrote in the letter, yesterday was my 21st birthday, and at that age, Newton and Pascal had already acquired many claims to immortality. So there's 2 more names that you could write on, okay? This is interesting. In his 20s, Fourier got involved in the French Revolution and was imprisoned briefly in 1794 over an incident involving different factions of that French Revolution. In 98, he was summoned along with more than 150 other scientists to join Napoleon on his unsuccessful campaign in Egypt. So quite a story for a mathematician who was debating whether to be a priest or a mathematician, became a soldier, but actually more as a scientist. He fought in the French Revolution, got involved with 2 factions that were fighting each other after the revolution. By the way, that happens with revolutions a lot. Look at South Sudan. I mean, pretty sad situation there. They broke away from Sudan, and then the 2 factions there started fighting each other, and they have almost brought the country, almost destroyed them. So I don't know what's going to come out of that one. But what gave rise after that? A dictator. Napoleon rose in the ashes of the, in many ways, failed French Revolution. I mean, they succeeded in overthrowing the monarchy, but they sure couldn't govern very well. About the only good thing that came out of the French Revolution, and I'm not sure it was the product of it, but it seemed to come about at the same time, was the metric system. Okay, that did come out of it, so scientists did have some play. But, boy, the country was a shambles, especially with the infighting of factions. So Napoleon, a dictator, rose pretty powerfully too, and then Fourier fought with him. Okay, not fought against him, but was there. But then he came into his own as a mathematician when things finally settled down in his 20s. He's more famous. I didn't know he had done the heat equation until I read this a few years ago. But the Fourier transform is a really, really amazingly powerful tool to study just by any kind of functions, not any kind, but a lot of different 1855, many years after Fourier had died, German physiologist, not even a physicist, physiologist, Adolf Fichte, showed that the heat equation describes not only heat conduction, but a wide range of other diffusion processes, such as osmosis, ion transport at the cellular level, motion of pollutants through air and water. So it became a basic tool in chemistry, molecular biology, environmental science, and it's called Fichte's second law. So two completely different individuals overlap 1 year in their lifetime, of no consequence there, but they contributed first to heat, but then he broadened it, Fichte broadened it to a lot more. So he's a potential paper topic as well. All right. Do you want to do preliminary questions? Yay or nay? Yeah, let's do them. Okay. Good blank piece of paper almost to write on here. Screen. Patricia derived the following incorrect formula. I sort of don't like this. By misapplying the product rule. Here's what she was trying to do. The partial with respect to x of x squared, y squared. Okay? You tell me what that is. 2x, y squared. That's the correct answer. Okay? Now, what she did was this. She said it's x squared times 2y plus 2x times y squared. Or y squared times 2x, doesn't matter which order you do it. That's how she tried to do it. What was wrong with hers? Say again? She's trying to do the product rule, but even what's wrong with that? Say again? A full derivative? Is that what you're saying?
Yeah.
Instead of just the
Partial.
Oh, okay. I think I understand what you're saying. I wouldn't quite phrase it that way, but I think I understand.
With respect to y in the first one.
Okay. Yes. A partial with respect to x has no variation in y, so don't take a partial with respect to y. That's her error. Without that in there, you have the same answer. Okay? But she even did that wrong. Because this is a partial, the implication is that x and y are independent of each other. If you have partials, you have to have two or more independent variables. Since the only two variables you have are x and y, you assume they're independent. Now, if you were saying that y depends on x, like we used to, y is a function of x, then what she was doing is almost right, except for one thing there. If this were, okay, if y was indeed a function of x, there's only one independent variable, and y is a dependent variable, then if you did d by dx of this thing, x squared, y squared, where y depends on x, they're not independent, then you would do exactly what she did, almost. You would take x squared, the first, times derivative of the second, which would be 2y prime. That's called implicit differentiation, remember? Plus 2x y squared. Okay, 2x y squared. Okay? That would have been correct if y was a function of x. But if y is not a function of x, if they're independent of each other, that means there is no x dependence on y. What does y prime stand for? dy dx, right? Well, dy dx, if they're not dependent on each other, that's zero. There is no change of x for a change in y because they're not related. They're completely independent. So this thing's zero, and you still get the right answer. Okay? So that is wrong. If she was trying to do implicit differentiation, she left that off. If she was trying to do partial differentiation, which is what you're supposed to do, there is no dependence on y. which would show up here if these are independent of each other, y prime, dy dx is 0. Because there is no change of y per change of x because they're independent. That's what it means. All right, I think that's what was her mistake and what is the correct calculation. You gave me the correct calculation first. Let's see what the book said her mistake was. This is 14.3, preliminary question. All they gave was the correct thing, which is 2xy squared. They didn't say how she made her error, but by not getting that answer is how she made her error. Okay. No. Number 2. Did I kill that one, or is it okay? Beat it to death? Okay. Yes. No, yeah, no, I wouldn't say that. Okay. Explain why it is not necessary to use the quotient rule to compute this. Is this almost the same question? D, the partial with respect to x of x plus y. I'm getting lost here. Okay. Partial with respect to x of x plus y over y plus 1. Okay. I was going all over the page. Okay. Is it necessary to use the quotient rule there?
With respect to x?
Yeah, if you're taking the partial with respect to x. No. In fact, they don't ask for this, I don't think. But if I were doing this problem, I would do it this way. Partial with respect to x. I'll break this into two pieces of x over y plus 1 plus the partial with respect to x of y over y plus 1. Okay, those are two things. This plus that, right? Okay, and what's it, and this? What would that partial be? 1 over y plus 1. What would this partial be?
Y over y. That would be 0.
0, because that's a constant. There is no x and y dependence there. So yeah, that would be, they didn't ask for that. Okay? Now, should the quotient rule be used for this? Partial with respect to y of x plus y over y plus 1. Yes, you'll have to. So split it up the same way we did before, or not. You can just do it like this. You've got to use the quotient rule because you got low d high minus high d low. No way around it because you're taking with respect to y, you got y in the numerator and the denominator. Can't get rid of them. So do it to it. Okay. That one though, with respect to x, you only have x in the numerator, so your denominator is just a constant. So you don't need a quotient rule. Good deal. Do they even have that in the back? In this case, the constant multiple rule can be used, and the second part, y appears both in numerator and denominator, so the quotient rule is preferred. Almost necessary, but they say preferred. All right, 3. This is 2. Can I get 3 on here? Y'all know, I don't think so. Okay, this is 3. Which of the following partial derivatives should be evaluated without using the quotient rule? Boy, they're all over this, aren't they? Okay, the first is the partial with respect to x of xy over y squared plus 1. B is the partial with respect to y of xy over y squared plus 1. And C, the partial with respect to x of y squared over y squared plus 1. Okay. Which of the following partial derivatives should be evaluated without using the quotient rule? A does not need the quotient. Wait. Yeah, it does not need the quotient rule.
B does need
the quotient rule. fact, what is C? 0. Okay, very good. So A and C don't need the quotient rule. Okay, that better be what they have back here. A and C they did. Good for them. All right, number 4. I think we can get this one on the page. What is f sub x where f of xyz is equal to, boy, there went our easy ones, wasn't it? Okay, sine of yz e to the z cubed minus z to the minus 1 Now, if I'm reading that right, the square root of y is down here on the same level with z. Is that how you're reading it?
I'm reading it as the same level as e.
Z to the minus 1? Huh?
It's not in the exponent.
It's not in the exponent.
Right.
Okay, so it's down on the same level with the e.
Right.
Okay, that's what I was seeing too. But I wanted to make sure. Huh?
It doesn't matter anyway.
Okay.
Either or.
All right.
It's the same answer as C.
Yes. What is it? 0. Because there is no x dependent anywhere in the problem. So 4 had better be 0. Good for them. Okay. Number 5. Assuming the hypothesis of Clairaut's theorem was satisfied, which of the following partial derivatives are equal to f sub xxy? Okay. The A is f sub xyx. B is f sub yyx. C is f sub xyy. And D is f sub xyxx. Okay. Which is the same as listed there? A certainly is. B and C certainly are not, and D is. So A and D. Are y'all happy with that? A and D. Fantastic. Homework exercises. Do any of the odds 1 through 7. Do either 9 or 11 or both. Do any of the odds 13 through 39. There's a whole passel and a half of those. Do some of the easier ones, some that are a little more strenuous. Okay? Do either 41 or 43 or both. Do 45. Do any of the odds 47 through, 55. I would do several of those. And by the way, they opened the door for you to do something like a paper on heat index, wind chill factor, or wind chill temperature. These are all things that you hear about a lot, okay? And you might want to see how they relate to calculus. Magnetic declination, there's another possibility. There's your seawater density, that kind of stuff. Anyway, blah, blah. Any of the odds 57 to 61. Do 63. Any of the odds 65 to 71. And then any of the odds 73 through 83. And boy, there's lots of paper topics here, folks. I see a Laplace operator mentioned, also harmonics, okay? And then I also see the Korteweg-de Vries equation, okay, which arises in the study of water waves. If that's an interest of yours, go for it. One sort of bad thing about that problem is it deals with a hyperbolic secant, which I don't particularly care for, but if you're interested in it, you might be able to see either how to use it simpler or whatever. Okay, any questions on 14.3? Okay. Let's see what's next. Okay. What have we got? 6 more minutes? Okay. All right, so let's get out of this and at least introduce 14.4. If it'll come up. Didn't quite get to finish lunch today, and I'm beginning to feel it. Okay. All right, now we're down to 5 minutes, but I think we can still get a little bit covered here. All right. Differentiability and tangent planes. Okay. Let's back up a little bit and think of when we were first doing functions. And the first thing we did with functions was take a derivative. Derivative defined the tangent line to that function, right? The first derivative gave the slope of the tangent line at that point, right? Now that we're talking about functions in 2 or more variables, independent variables, you're talking about an area down here. So what you have is a surface up here, and the surface now has a tangent plane, not a tangent line. The plane needs to be planar to, tangent to the curve in every dimension, especially you're given 2 dimensions. Okay? Because we try to limit that to 2 dimensions. It's a 3-dimensional picture. Okay. So, well, let me blow this up a little bit. You can see it, maybe the folks at home can see it better too. That is your pictorial representation of this. In this section, we generalize 2 basic concepts from single variable calculus, differentiability and the tangent line. The tangent line becomes now a tangent plane for functions of 2 variables. Now, if you have functions of 3 variables, man, what you got then is a tangent surface, and I can't even imagine what that looks like, okay? So we're not going there yet, maybe at all. So in two independent variables, you have a tangent plane. 1 independent variable, you have a tangent line. Okay? Now, intuitively, and this is what this picture is, we would like to say that a continuous function f is differentiable if it is locally linear. New concept here, locally linear. And by the way, I look outside, and this is the first time I think I've seen bright sunshine today. But also, I bet you, if my understanding was right, the temperature is dropping. Okay, so when it was cloudy, it was warmer. Now that it's sunny, it's colder. That's because of the front passing through, by the way, but it has nothing to do with calculus. I was just getting the glare. I didn't know if Matt was being bright over there or, okay, whatever. Okay, that is if its graph looks flatter and flatter as we zoom in on a point P, AB, f of AB. Eventually becomes indistinguishable from the tangent plane. Now, what does that mean? Okay. What if this was your surface that you had in, okay, blow this up. Okay, let's see if I can get it all in one screen. I think I can. Barely. There we go. Close anyway. So what if we had, this was our surface. Your XY plane is down here, there's the surface there. Now that looks pretty, actually it looks like a mountain range to me, you know, folded mountains perhaps, okay? Peaks and valleys, no sharp peaks, rounded peaks like the Appalachians or something like that. The question, the concept is this locally linear? Well, obviously looking at that is not very linear at all. It's very rough. But if you took just this little piece of this and blew it up into a shape about like that, so to me, myself, why did they show a circle here? Why didn't they show a rectangle here? And then that would look more like this. Well, this thing that looks like it's going everywhere, when you just blow that part out, now this is getting, it's looking a lot more normal, sort of, a little flat. Blow this up again, keep doing it, and if you get a big enough area around here, that almost looks like a plane, okay? If you picture yourself, if you climbed any hill, say, okay, and that sure doesn't feel like a plane then, but if wherever you're standing, and this happens to be sort of near the peak up here, if you're right near the peak and look around and everything's falling down, you don't feel like you're a plane. But if you look a little closer here, it's just falling a little bit, and then you look just right below you, that's almost flat. That's what we mean locally linear. If you keep zooming in on it, if you wind up that it gets flatter and flatter, then it's said to be locally linear. Yeah. 5 minutes still on? Okay, I guess that's all we could do. No new homework assignment on 14.4, okay? But we'll pick up next time if I can find my pencil, which once upon a time I had over here. We will start next time with, I guess, 15.3. Figure 3. All right, have a good weekend. We'll see you. And get those papers into me, those who haven't done it yet. I think y'all have. Boy. Where is local linear?